Okay, so we're really lucky to have Tim Koslowski here. It almost didn't happen because of the sorry? Oh. Yeah, but no, because of Mexican logistics. But anyway, it's great to have him here. Anyone who's ever worked with Tim knows that he's absolutely brilliant. For those of you who haven't worked with him, he's the kind of guy. I remember when we were doing shape dynamics. There's ever a moment when everybody is really confused. Basically, everybody at the exact same time would look to Tim and say, Tim, what do you think? And then he would always save us. Anyway, so today he's going to give us a really bottom-up version of his vision for shape dynamics.
Okay, well, thanks. I mean, I have to say about the same thing that Astrid was saying yesterday about the introduction. I don't think I can live up to what Sean was saying, and but I hope that it's still useful for you all to listen to this talk. I'm going to talk about what I'm going to talk about today is what I think is a good formalization of the philosophical or foundational ideas that Julian has put forth in his talk, and using a lot of the machinery that Sean has already introduced at the intuitive level. And the purpose of this talk is to make this, to turn this into much more of a formalism. And the reason for that, or at least for me, the reason is that I wanted foundations for a theory of quantum gravity, or what to look for in a theory of quantum gravity that is based on Julian's ideas. And to be able to do that, you need to be quite specific in what you want from this theory. So, since a good part of the audience is are philosophers, I have a one-slide review of relationalism, and this is basically to pick up what Julian was saying yesterday. So. And we had this discussion several times already during this workshop in private with several people. If you want to describe lab situations, laboratory situations, you never have a problem referring to reference structures, because there's a huge world outside, and we can use absolute reference structures that are just there and that provide us with scales and with enough reference structures to never have to worry that a law that we want to test, or whose consequences we want to test in an experiment, is really disentangled from the definition of what the physical objects are that enter into the definition of the law. But this comes back when you want to describe the universe as a whole, because if you want to describe the universe as a whole, we have to be aware of that all these reference structures that we can just use the definition of what is a second, what is a meter of say a frame of reference, or even a preferred system of coordinates that are given by the table in a tabletop experiment, for example. They're all really physical objects within the universe. And the idea of my version of relationalism is that the objective description of the universe can only can only describe, in principle, the relative change among relational quantities. And what I mean with that is that, first of all, I don't have any absolute quantities. I have to always, physical quantities are always comparisons between two between the properties of a reference object and the physical object we want to inquire. And then we can, that implements what Julian would call spatial relationalism, or the spatial part of relationalism. And then we can only objectively talk about the relative change amongst them. So when one of these ratios is changing, we can say, while this is changing that amount, a different ratio has to change in another amount. So what I like to, I had this example on my slides for quite a while, because it really illustrates when you're in doubt that we're always talking about ratios. For example, when we say that 1 second is passing, or a distance is 1 meter, then we refer in effect to a ratio that is given by a reference structure, the cesium-133 atom, and then a certain number of oscillations of the hyperfine transition of the, and that defines a second, and the speed of light then in vacuum defines a meter, and we're really talking about ratios between a reference object and whatever we want to describe as it. So, as a first step, and this is, I think Sean was saying something, just one damn shape after another, I think it was the expression, or something that I would never say, but
I said it first.
Okay. You were probably inspired by Bryce DeWitt in saying that. But that the objective description of the universe is only a succession of relational configurations, what Julian likes to call shapes, and we've taken over this word. And what this means mathematically is that we want to have an equation of state for when we want to describe the universe, or the dynamics of the universe. The best thing we can do, we cannot do in principle when we take this relation of first principle seriously, we can in principle not do any better, or not be any more ample in our description than giving an equation of state for the intrinsic geometry of a curve in relational configuration space.
What do you mean by equation of state?
I will come to that, and you will see, I will go through an example in 2 or 3 slides to give you, so basically how the local geometric properties of the curve are changing when one of these properties is changing, how the other ones are changing. That is what I mean with an equation of state. So
what's an example of a non-relational? I mean, the general impression of this meeting is that this is something new, and I believe it is, but it's supposed to correct something old, which is...
Yeah, and I will come to that, because I will do this in a few slides. I will go back to this to the Newtonian toy model, and then, because there you can do it in 2 slides and you can beautifully show what is going on, and where we get rid of the reference structures that is in the canonical description of the n-body problem, and we describe only the intrinsic geometry of the curve that is traced out by the relational quantities. So, with that motivation, I can give you the plan for the rest of my talk. So first, as I just announced, I will do some derivation of what this, starting with the Newtonian n-body problem at 0 energy. I will give some derivation of the equation of state for this curve that I want. And then I will give you a preliminary geometric interpretation of what the objects that appear in my equations mean, and say a little, just a few words about the relation to the standard phase space. And Dave has, I suppose he will talk in a lot more detail about that. And then in a second part, I will talk about the identification of geometric structure. So what this equation of state, so this, what it is, what the phase space or the space of local data that I need is, and I will show you this in two examples. And you will see how, in the meantime, I will have 2 or 3 slides about how this goes, how this can be applied to GR. And you will see that that general relativity basically falls into this description. In my abstract that I submitted a couple of weeks ago, I was way too ambitious, and I wanted to cover a lot more, and then I realized that I just have an hour to talk. So the whole thing is, of course, that I want to find foundations for quantum gravity, or for postulates for what a theory of quantum gravity should do. But to fill that with more detail will just be too much. So Julian's picture, or Julian has this amazing ability that he can look at a problem as simple as the simplest non-integrable system, the Newtonian 3-body problem at zero energy, and can deduce a lot of structure, and that was very inspiring for me and for all of us who have been working on this. So let's start with, if we have 3 particles, and we say this is an island universe, we don't have any more than these 3 particles. We need to say that what is perceptible in this universe are the distances between the particles. If we had gotten rid of that from the beginning, we would have nothing left. But then there is, in particular, there is no origin, there is no reference frame, and there is no time scale, and there is also no length scale outside the system. So we want to get all these reference structures from the dynamics of these 3 particles. And then, so what the particles can only do is they can, as Julian was pointing out yesterday, they can only change their shape. And so if the dynamics is the change of the shape of this triangle here. So, and then what I want to describe is how one of these angles that defines the shape of this triangle is changing when another one is changing by a certain amount. And this is what is in here. So if we look at a typical 3-body solution with 0 energy, then you see, well, if it has.
Are you assuming these 3 angles add up to 180 degrees?
Yes. Yes. So
why? Because it's a curved space.
No. I'm saying I'm taking the simplest model. I say we're in a. This is in a Euclidean geometry. This is why I was saying the lengths here are perceptible. So I have some, and I suppose that I can parameterize the length ratios as angles.
Perceptible meaning?
Meaning that this is what is really, this is what I can know about this universe. This is what is.
But that involves you outside the 3 bodies.
Yes, you're right, and in a sense, yes. So this is true, and if I may take a minute to explain on that point. Of course, when I go back to these relational first principles, then I would want to model myself as my perception within this. But the best thing I can do, in the best of all worlds, I can never do better than getting away with all the reference structures. This is, so to say, the upper limit of information that I could have about this.
These are heavy particles and you are a light particle.
Maybe, or if if you're happy with that, I want to describe a mathematical model in which I don't worry about what the perception is of, or how I model my perception within this. This would be, in a previous version of this talk, I spent about 15 minutes to explain how my perception would come about within this, but the focus of this version of the talk is quite different. So what I say is the upper limit of information that I can have about the system are the length ratios that I draw here. So if we start with a zero energy problem, then to add up to zero energy, I must have a bound system and some free particle. The relative kinetic energy of these two is always positive, so the bound system has to have negative energy. So this is what is drawn here as a curve where the red and green particle are orbiting each other, and they're scattering with the blue particle. And then this is a fairly simple interaction. This could be a lot more complicated. This could go around for quite a while here. But then what will happen is eventually another pair will be ejected and another free particle. In this case, there's a exchange of the free particle. In other cases, this doesn't happen. So I want to describe this situation, a typical three-body interaction at zero energy. I want to describe this simply on shape space. So how these angles or how these length ratios are changing.
Just one comment. Of course, zero angular momentum is also.
Yes, I wrote it here, and I didn't mention it in words. Yeah, you should. And angular momentum would be visible in this curve here, even if I do the projection to shape space, even if I do the projection to the space of angles, of only angles. What happens is Julian introduced the sphere, which is when you have three particles in 2 dimensions, the shape space, so when you configuration space modded out by translations, rotations, and scale transformations, attains the topology of its.
Where's the blue one?
So about no, this is the colors of the curve on the sphere do not indicate the colors of the particles. So one point on the sphere here describes one particular shape. It describes that the blue particle is here and the red and green particle are here. So this would be maybe here somewhere. Yes?
Is there a simple way to get the angles of the triangle to the angles on the sphere, or is it?
In formulas, if you spend about one slide, it's straightforward. So basically, what there is this work. There is this work by Littlejohn and Reinsch about molecular dynamics, and basically the first step is you mod out by translations. This can be done by going to Jacobi coordinates. Then you mod out by rotations. This can be done by going to inner products between Jacobi vectors and triple products. And then at the end you mod out by scale transformations. So you put in a constraint on the size of the squares so on the length, on the sum of the length squares of the Jacobi vectors. And if you work, yes?
So you can do this for gravitational forces, but if it were really molecules and atoms, you couldn't do it.
That's right.
Depend differently on the
That's right. That is right, and that is why, because at the end I will base what I demand from a quantum theory of gravity on the intuition that I get from this classical system, and that gives you quite distinct phenomena than in molecular physics, where you have an atomic length scale, and this is the reason why you cannot mod out by scale transformations in that case. So now I want to do that. I want to start with the Newtonian n-body system at zero energy, zero linear momentum, and zero angular momentum. And for simplicity, I will be a little lax in my description and not show you how to mod by how to do the modulus by rotations and translations. Just trust me that the formulas would not change in a drastic way. And so you get the right idea. If I write down Newton's equation, so the change of the coordinates with time are the momenta divided by the mass, and the change of the momenta is minus the gradient of the potential. So now what I need to do is, when I want to get rid of these in the system, I need to pull out one of the I need to pull out the scaling quantity of the particle position. So one thing that you can do is the root mean square size, or you could do the mass weighted root mean square size, what Julian was presenting yesterday, and the virial, so the inner product of the momenta and the particle coordinates. And so this then defines an intrinsically defined length scale, that is, at every moment this island universe has a particular size given by this r, and it has a particular unit of time that is basically defined that is indirectly defined through this virial at a given point in time. And then so I separate those two degrees of freedom out from the positions and the momenta, and I have then remaining coordinates for the that describe only the shape and the momenta conjugate to this shape. Now, in the Newtonian n-body problem, I also have through the kinetic term here, I have a preferred metric on shape space, and this is obtained simply as the kinetic term in the action for the Newtonian n-body problem, and then this action would scale, the metric would scale with r squared. So I just divide by this scaling with respect to r squared, and I get a metric on this shape space, and I can explicitly calculate it. And here I just wrote it abstractly, but in whatever coordinates I choose to put on shape space, I get a metric on this on shape space. And then the idea is to describe the curve as a first step in arc length parametrization and not in time parametrization. So if I do this, and if I look at the first equation here, and I say, how does the shape change when I do a step in a direction in shape space? Well, the only thing that can happen is that it changes in the direction of a unit tangent vector, unit with respect to this metric, and this tangent vector is specified by a direction by some angles on shape space. So if I, since I want to...
Where did GAB come from?
GAB comes from the kinetic term in the action for the Newtonian n-body problem. And basically when I rescale it by the total size of the system, then it projects down to a metric on shape space. That's where it comes from. So it is not a metric that gives you the size of any physical object. It is a metric that tells you what is the amount of change of shape. So it's a quantification of how much change of shape is occurring when I do.
Is it trace-free?
No. No, this metric for coordinates on shape space, the Q's are coordinates on shape space, is just the Riemannian metric on that on shape space, and it is just quantifying. It's just assigning a number to every step a number that says it's this amount of change of shape when I do a step on the curve on shape space. So when I go from here, from this point, I make a tiny step to here. It assigns to this step a number.
So I think you should just make clear at this point you're trying to just describe basically Newtonian dynamics in a framework that is just in the shape space. So he's not trying to model a general dynamical system in curved space-time or anything like that. No, just to...
So the point is to get rid of the S.
The point is to get, so with this I got rid of the, with this I got rid of the T's already.
Yeah.
So, which is, I don't want that in the background there is time flowing while nothing is happening.
Yeah.
So this is why I first do an intrinsic parametrization, and then at the end I basically forget about the parametrization and I just look at the ratios of the Q's, the phi's and so on, what we will find. So when I do that, then I can parameterize the direction, these angles, when I come from the Newtonian model, in terms of the shape coordinates and their conjugate momenta, and use Newton's equations and when I for how these angles are changing, and if we just do all the replacements in here, then you get this equation here. And what you see here is that, well, here you get how an angle is changing with respect to a shape. That is good. That is a unit tangent vector. That is also good. But here you see how an angle is changing with respect to a momentum. And these momenta, because it's just a canonical transformation, they have the dimension of an action. So these are dimensionless, so they have the dimension of an action. And then you see here, this bracket here also has the dimension of an action. This is basically because there are derivatives occurring here. And what I need, and this is also how dv dq appears and the 1 over p squared.
Can you clarify the relation between big phi and the small phi?
Okay, so I start out with the Newtonian description, with the description where I have an absolute coordinate system and where I have an absolute time. And there I just split the variables in Q's and P's. The Q's are dimensionless shapes and the P's are their momenta, but they still have dimension. Now I want to get rid of this dimension because I don't want this in my description. So I describe only the direction in shape space. So when I do that, I can take any representative of this direction and I see how when I'm at a particular point Q and I have a momentum of P, what direction it's pointing at. So it is just this functional dependency, capital Phi. The lowercase phi is then the dynamical variable that I want to use because it is the dynamical variable that describes the direction on the tangent direction to the curve. So what is then, and what Dave will talk in a lot more detail and with a lot more physical interpretation about, for me it's just a curiosity. It is a curiosity, but it has a physical effect. If I rescale, in a Newtonian system, if I rescale the coordinates by a constant factor, and if I divide the momenta by the square root of this factor, I rescale t by t to the 2/3 of this factor and the energy by 1 over this factor, then a solution is mapped into a solution. Now, the point is, that if I'm just interested in describing the curve on shape space, what is described by a constant dilatation of all coordinates is something that projects to the same point in shape space. So this here projects to the same curve. If I make this picture 10 times larger, I still get exactly the same curve here. But then so the momenta change, the time changes, but then then the energy also changes. So if I have a system where I have energy 0, this last equation is trivial, and I can use the similarity to set one of these, for example, the total size of the momenta, to a reference value. And that is the trick how to decouple one of the degrees of freedom. So the evolution projected onto shape space becomes independent of one of these degrees of freedom in the energy 0 case. So now I gave you this formula here, but I already criticized it because there are still dimensionful quantities that enter here. But then I realized that I can write this. The potential is a coupling constant times something that depends only times a function that depends only on the shapes, and that is the same function c that Julian has been describing yesterday. And in the Newtonian case, it's divided by 1 over r. And then we see that there is another dimensionless ratio that comes in, which is the total size of the momenta divided by alpha, this coupling constant, and r. And so I rewrite the previous equation for the change of direction just in terms of this kappa, and I obtain this equation. So now I'm happy with this equation. I have described everything in terms of, I have described relational change for the shape and for the direction in terms of something that is intrinsically defined. But I have this additional degree of freedom kappa. And now, to close the system, I need to calculate its dynamics. So I do the same thing. I plug it. I use the Newtonian definition. I obtain this right-hand side, and then the total dilatation of momentum divided by the size of the shape momenta appears here. This is the only. This is a dimensionless ratio, but it's not independent when I already impose that it's energy 0. So I can solve the energy 0 condition in the Newtonian model for this ratio, and I obtain this square root here. And this plus or minus here might bother you if you're because you say, oh, these equations are underdetermined. But basically what we will argue is that you should always take the plus sign if you want to describe the perceived direction of time. And this has something to do with something that Julian and Flavio and I have been doing about the error of time and how the error of time is in this particular model can be obtained by simply looking at in which direction the system is clustering, in which direction.
If the square root is 0, is that the Janus form?
Essentially, yes. It's, yeah, it is. Yes?
Maybe I'm not saying, but what's normal pi? Because I thought it was...
So pi is the, pi are the momenta here, and it's, so it's the square root of the kinetic energy, essentially, and then I have something that is the dilatation momentum, this virial, which has the same dimensions, and so I get a dimensionless ratio here. It's essentially, it's a kinetic energy. It's a kinetic energy in the change of shape. So there are two kinds of kinetic energy. One is in the change of size, and one is in the change of shape. And it's this ratio between the two. So what I get is is a parametrized form of the equation of state of the curve. So this is okay. So I have dq. I have the change of the shape is just the unit tangent direction. The change of the direction is some equation that I can express in terms of the shape, the direction, and this kappa degree of freedom. And then this degree of freedom has also its own equation of motion. Now we had one degree of freedom decoupling due to this dynamic similarity, but then the scale and duration basically decouple only due to dimensional homogeneity and energy conservation. So energy conservation allows me to do this step here, to eliminate this ratio, and dimensional homogeneity is just saying if I start out with the dimensionless change. So if I just start out with how is the shape changing when I change the total amount of shape, how is one of the components changing, then this is dimensionless. So the right hand side is dimensionless. So all the dimensional quantities have to decouple, and when I want to close the system, anything that can appear on the right hand side has to be dimensionless. So this is why the last dimension full quantity that would be in there decouples automatically. So let me go to a preliminary geometric interpretation. So I have a system that describes the intrinsic geometry of the curve, that describes how the shape, the direction, and the direction are changing. And now I want to argue that this kappa here is really just the curvature of the curve at this point. So I'm really just describing how the intrinsic geometry of the curve is changing as I'm going along, as I'm doing steps along the curve. And you can see this very practically, basically by taking the second covariant derivative with respect to the kinematic metric that I used here of the curve of the coordinatized version of the curve, and I calculate the size of the acceleration, then I see that this extrinsic curvature of the curve is some factor that I can specify. It's written over here, times kappa squared. But if I had used a different metric, a conformally related metric to this one here, then I would have obtained a factor of m that is just equal to 1, and so I can identify this kappa as the curvature of the curve with respect to a particular metric. So this is what I meant when I said I want to have an equation of state for the geometry of the curve in shape space. This is how I want to do dynamics. So here I just want to, I put this slide in last night because Julian was saying that I have equations that once you integrate this curve, the equation of state for this curve in shape space, you have forgotten about you have now forgotten about the total size and the increment of time, of Newtonian time, but you can recover them, and they're basically parasitic equations. So if I start out, if I have 3 points on this curve on shape space, if I start out in point A, and I define at point A the size of my universe, of my island universe, is x, and I take this as the definition of my unit, then I can use this equation here and integrate it along the curve to see how is the logarithmic ratio of r divided by x, how is the size of the universe relative to this definition A changing, and I obtained something that just depends on the shape. So it is just a parasitic equation. It has no life of its own. The curve has completely decoupled, and I can also calculate the Newtonian time in terms of a time interval that I define between A and B, for example, and then I can measure intervals between B and C in this unit, and this is then just obtained by integrating this equation, which again is just an equation that depends on intrinsic geometric properties of the curve. So this is how it formally how formally you can go back to the scaled description. And basically, what happens when we consider Bianchi cosmologies and we look at the Big Bang, we have the same thing happening. We have an autonomous system of this sort that describes the evolution of the shape of the universe and the dimensionless ratios of matter degrees of freedom. And then we have and this system can be integrated by itself. And then we have an equation, a parasitic equation for the scale factor that is exactly like this one, and a parasitic equation for proper time that is exactly like that one. And what happens at the Big Bang is just that this equation diverges. So that the logarithmic derivative diverges, so this means that the ratio goes to 0. So it's not a problem of it's not a problem. The Big Bang is not a singularity in this system, it is only in this parasitic equation. It's a problem. So Dave will talk a lot more about the relation between phase space and the phase space of this curve. So I will not go over this in detail. And Sean already gave the foundations of what you need, what are the technical requirements to apply this to general relativity. The obvious problem is that the canonical description of general relativity, you don't have a preferred time variable, and so you have the choice of foliation is a gauge choice in general relativity, and you have to use this. You have to use the symmetry trading, that you can fix the foliation and obtain, and by fixing this foliation and not changing the physics, you gain a conformal invariance, but you don't change the dynamical system that describes GR. So this is a very old slide that I always showed, which is you have general relativity with a constraint surface that is, and I indicated gauge orbits here by lines, and this is the constraint surface that is given by the scalar constraints of general relativity, and this purple line here is a particular gauge fixing of foliation, is a particular choice of foliation, and then I see that I can dualize that to a theory that is conformally invariant and that has a particular choice of scale in the dual description. So I can now basically, I'm running out of time, but I can basically turn the crank, and once I have traded the symmetries, I can turn the crank and do the same thing for general relativity that I did in the n-body problem. But it turns out that there is a more efficient and more direct way. Once I have found initial data for general relativity, I can do the following. I say at an initial time I define a reference density that is just the volume form of the metric, and I define the trace of pi just being normal trace of the metric momenta. And then on the right hand side here I have the conformal metric, so this is the metric divided by 1/3 of its.
So now it's a density.
So this is a density of weight minus 2/3, the conformal metric here. But I have another density, so I can always put these two back together to obtain the metric. It's just that this I will treat as a background structure in my equations, and this is the dynamical variable in my equations. And then the trick for decoupling is basically that you impose that this gets a trivial equation of motion, so that this is only homothetically expanding, and that its structure is not changing. So that so this is what I wrote here, that the time derivative of omega, of this reference density, is just a function of time, but it doesn't depend. This would be a scalar, the logarithmic time derivative, that it doesn't depend on space. Then I have everything shuffled into the scaling of a total volume. And I can use the same trick that I used before to decouple the total scale R here, that I have here, to decouple the total volume from the system. And that's basically what I do, and after some work, and
Can you go back one slide?
that's basically what I do, and here are just the definitions of various quantities, but basically I want to describe how a curve in conformal superspace, so something that is given by this.
So you use the reference density at an initial time?
Yes. I take that from one initial time. I take this as fixed. And once I do that, then I can get a set of decoupled equations for GR that describes basically the conformal geometry, the direction in conformal superspace. This is. If I had more time, I would go through the definitions to explain to you why this is a direction, but. And I have again a curvature degree of freedom, which is this thing here. Its physical definition is that it's the trace of the extrinsic curvature divided by the total energy in gravitational waves. And this is again related to a curvature degree of freedom of the curve on conformal superspace. And these equations describe a general relativity, the curve that is traced out in conformal superspace by general relativity intrinsically. So now I'm unfortunately not having a lot of time. So what I want to say in these last, say, 2 or 3 minutes is that this has all been worked out in an explicit coordinatized representation, but there is a whole geometric picture behind this. And basically, it is that I can find a phase space, a space of this space of variables that appear here, just as variables as rho, sigma, and kappa. They form up to a phase space, which is the space which is the space of these local geometric data. And just to give you a hunch what it is, I will explain it in the simplest case, which is when you have free particles. And let's say we have 3 free particles in 2 dimensions. Then, as I said, the shape space is just the unit sphere. And if they're free particles, then they're it's just geodesic motion with respect to the kinematic metric. So basically, they will just trace out great circles here. So then the equation of state becomes, well, the change of shape is just a unit tangent vector defined by a direction, and the change of direction is just the representation of the Christoffel connection on the unit tangent bundle, on the tangent bundle where I restrict myself to the unit vectors contracted with the unit tangent vector. And to show you that this is not a simple, that I could not have seen what comes out if I had just worked with coordinates, I show that the unit tangent, or well, those of you who have thought about that know it, that the unit tangent bundle of the two sphere is the Hopf bundle. So it's a projection from the three sphere down to the two sphere, and that I didn't know that before I actually went through the equations. But here, so here's a depiction of I took this from Wikipedia of this projection of the three sphere to the two sphere. So imagine you foliate the three sphere by circles with different colors, and then each circle of a particular color projects down to a point of this color. So this whole circle here in the three sphere projects down to this point on the two sphere, and so on. And the circles are linked in a globally in a non-trivial way. Locally they're unlinked, but if you take the entire three sphere, you cannot unlink them. You cannot move them out without deleting one of these circles. So then for the Newtonian n-body problem with zero energy, I have this additional curvature degree of freedom, and basically I can do a construction, and it took me way too long to get this construction right. And basically you get something that is a little larger than the unit tangent bundle. You get a unit tangent and acceleration bundle. So you get also the second derivatives with respect, the second covariant derivatives with respect to the arc length metric enters in the geometric structure. And then you have a purely geometric equation of state. And what I want to point out here is that this is not when we usually talk about equations of motion, then we talk about it in a canonical language. We talk about them that they are a vector field over phase space. So they're Hamiltonian vector field over phase space. So they're sections in a tangent bundle over phase space. But if we are in a system where we have if the tangent bundle is a cotangent bundle over a Riemannian manifold, then we can canonically identify it with a canonical derivative action of the directions in the tangent space over on configuration space. So this is something that is canonical. This is just kinematics. There is no dynamics in that. And the same thing happens here, but just that it's not just for the directions, but also for the acceleration. And that so with that I get an additional restriction to what equations of motion have to look like. They have to have this canonical structure as basically given by inverting these definitions again. So they are sections in the unit tangent bundle over phase space. I take unit tangent bundle because I don't want to refer to a particular parametrization. And the unit tangent bundle, by the way, is canonical. You obtain it by projection. You don't need a particular metric. You just need the linear structure of the fiber of the tangent space at each point. And so we have, and on this I impose that I have the canonical derivative action of the directions on base space. So all of this in short is just saying I have you give me a particular shape space, and I can tell you what is the phase space over this shape space, and what are the possible equations of motion over this shape space. And then, of course, building a model is specifying one particular one of these. And so if I, my summary, well, the first 3 points are basically that, that I reviewed the relational considerations of Julian. I applied them to first to the n-body problem, but then I also showed, at least in words, that you can do this also for the evolution of conformal geometry, and this becomes locally indistinguishable from the dynamics of general relativity. Then when I integrate the system, this is what I didn't explicitly show, but what I have to argue in analogy with the Newtonian n-body problem. This doesn't generate space-time geometry, but instead space-time geometry is an effective description, and then Hickey was quoting how you can use matter degrees of freedom, how they move in this universe to basically experience what the space-time geometry is. But the main point of my talk was this last point here, that it gives me a set of postulates for what I want from what I should look for in a quantum gravity version of shape dynamics. So I want to have a shape phase space for that is basically this direction acceleration bundle, and I want to have equations of motion that satisfy the axioms that I lined out before. And then what I look for in a theory of quantum gravity is one that in a semi-classical limit reduces to produce precisely these axioms.
We ate up most of the question time, but we started 5 minutes late, so we still have about 3 minutes for questions. Yeah. Okay, so we'll start with questions. Right. So let's do this question now.
Actually, I just worried about actually physical quantity in the scale invariance dynamics and the coupling constants. That it has a dimension, and also like energy and momentum. If we have actually scale invariance, we have to have a certain equation, like a covariant equation, under the scale change.
Basically, this covariance that you're referring to, and Dave will talk a lot more about that. That it is a covariant system, that when you change the overall units, that you have this dimensional homogeneity that allows you to decouple all when you just look at scale invariant quantities and you just want to see how one scale invariant quantity is changing with respect to another, then on the right hand side of that equation can only appear scale invariant and dimensionless quantities. So whenever I want to close the system that I start up here, on the right hand side I can only obtain scale invariant, dimensionless and scale invariant quantities. And this is precisely due to the fact that dimensions have to be homogeneous. I cannot add mass to energy, but I can only add mass to mass or energy to energy.
More questions? We've got Tony in the back.
Hi. I was just going to ask, is anything special here about the one-over-r potential, or could this work with any pairwise potential?
So there is nothing special with the 1/r potential. This is just something that happens that leads me to precisely this formula. Basically, this factor of 2 depends on the 1/r potential. It would be a different factor. It would be.
That's if it's a power law, but it could be.
It doesn't even have to be a power law. It could be any. It could be.
It would be just a factor there.
It could be a non-power law, but if it was non-power law, then there would be at least one ratio of coupling constants, more that I need in the equation. And this is when I write the potential in this form, I have only one coupling constant here. In something that is, for example, an exponential, I would have this one that gives me the units of energy. Then I would have another coupling constant inside of here that would then just be
like a molecular potential.
Yeah. So then I would have an R naught somewhere sitting here, also in that. And that has profound differences. Then then the system would not have. The system would become this. You can model the same thing if you have energy non-zero. If you have a non-zero energy, you have also added one more dimension full coupling constant. And then I didn't discuss this because this is not what is important for GR. A GR falls into this class, but if you have the non-zero energy problem, then you get one more equation. Basically, you don't just have the curvature of the curve, but you also have the jerk of the curve. So the second derivative of the tangent vector that appears.
More questions?
I was just trying to think if this would apply to electromagnetism. In other words, if you have both positive and negative charges.
It does. It does. So there's what in electromagnetism it only this function C here takes a different form. So this function C here for when you have masses, so all bodies attract one another, then this takes a form where you just have holes.
Okay, but then I think that the whole thing is extremely impressive and interesting. But presumably in the electromagnetic case, this cannot take into account electromagnetic waves in some sense. So
that's right. That's right. In this in this simple model, in the particle model, so when I do field theory, and if I take the Maxwell field, I can basically run this algorithm for the fields. But for particles, I can't. What you can do is, and this was actually something that Yuri Bonda has done. You can apply this to Weber electromagnetism. So where you have the Weber force, which gives you basically the first relativistic correction due to the magnetic field.
But this will eventually lead to the question of the gravitational waves to be included.
Well, the gravitational waves are in the description of general relativity, and basically gravitational waves, I mentioned that in passing somewhere. Basically there are that you have a non-trivial, that you have a non-vanishing change of the conformal geometry. So you have so that this is non-zero, and this is actually the case that we want to consider, that something that you don't have this globally zero, because this would be like Julian was saying, if our W smelts, but if you as soon as you have any perturbation on it. Well, I'm just not used to the British accent. I learned English in Texas, so.
We have only have time for one more question.
No.
I did briefly. Well, I was going to ask whether with something like EM, that the charge mass and the inertial mass aren't going to be the same, but is that going to be important here?
You mean if I look at the mechanical toy model, and because my claim was that only the form of this function here changes, and yes, if you have two forces, so electromagnetism competing with gravity, then something actually does change, and it's non-trivial, and it is that you have the ratios of decoupling constants that appears in there, and that gives one additional dimensionless that appears in equations, and I think they've come.
Time to discuss like some of the